For hundreds of years, people have been developing their understanding of genetics, and as it has evolved, scientists have made unbelievable discoveries. From creationism to natural selection and the understanding of genes, we have slowly unpicked the mystery that is our genetics. The topic of epigenetics is vast and cannot be fully covered within such a small time frame, so this documentary will only cover a brief history of genetics and the emergence of epigenetics, as well as studies that have shown the effect of epigenetics in organisms, epigenetics in humans, and how this information impacts us as a global community when it comes to our understanding of inheritance. Human understanding of inheritance has been slowly developing for thousands of years, but has picked up quickly in the past century. In 500 BCE, Hippocrates put forward his bricks and mortar theory that specific physical characteristics were given to children by their parents, if their parents had developed them in life before conceiving. For example, if their fathers had lifted weights and become strong, then his children would be muscular as he was. This theory later met opposition by Aristotle, as he argued that if a man had a child when he was young and had a full head of hair, but developed baldness later in life, the children could still develop. Lamarck proposed that the environment could affect how genes worked and that these changes could be passed down to future generations. This idea was scoffed at by the scientific community because at the time people firmly believed that nature and nurture were separate, and the environment could not affect genetics. Lamarck was on the right track, but the fault in his theory was his idea that evolution was striving for perfection, and that all adaptations of a parent could be heritable. When Darwin published The Origin of Species and proposed that natural selection was the driving force behind evolution, he saw no evidence that the environment could affect genes and disagreed with Lamarck's ideas. However, later in life as he continued his work, he wrote about the likelihood of the environment affecting characteristics in organisms. Mendel's study of pea plants has become what is now an incredibly influential study. By noting the characteristics of pea plants and their offspring, he discovered traits that were passed down by parents in what he called alleles. When people finally paid attention to his work, his discovery led to an understanding of dominant and recessive genes. When the Human Genome Project launched in 1990, the goal was to sequence the entire human genome so that doctors would be able to understand how genes influence disease at a genetic level. This would then lead to early diagnosis, better treatment, and prevention of diseases that had a genetic influence. Since the 1950s, the central idea behind how our genes function has been that DNA creates RNA, and RNA then makes the proteins which make our bodies function. This idea led to the assumption during the project that the majority of our genetic makeup would code for proteins. When the Human Genome Project was complete, scientists were shocked to learn that only 1% of DNA actually coded for proteins, and approximately 80% of our genome is used to regulate the expression of the genes around it. People used to believe non-coding DNA was useless because it didn't code for proteins, and so named it junk DNA, though they are formally named introns. Introns make up 80% of our genome and are so important because they control gene expression in the genes around them. They exercise this control through three mechanisms: methylation, the modification of histones, and the silencing of messenger RNA. Methylation is when a methyl group attaches to cytosine and represses gene transcription. It's thought that methylation occurs to assure that transcription cannot happen in genes that are already switched off. Histones are spools of protein that DNA is wrapped around, and the combination of DNA and histones are called chromatin. Chromatin has epigenetic markers which affect how tightly it's wound and how accessible individual genes are for transcription. In the year 2000, Randy Jertel and Robert Waterland designed an experiment to test the effects of gene silencing on agouti mice. These mice are susceptible to cancer, diabetes, and tend to have short lives. They changed the agouti female's diet so that it was rich in methyl donors. Methyl donors are molecules which attach themselves to genes and silence them. By feeding the pregnant mouse this diet, Jertel and Waterland managed to silence the agouti gene in the mother's pups. And when they were born, they were slender, with brown fur, and had none of the detrimental genetic problems that the mother suffered from. Daphnia fleas are interesting because they can develop into two forms depending on the environment they develop in. If they develop in water that has predators, then they develop a spine and a helmet. whereas if they'd grow in safe waters, they develop neither of these defensive body parts. This is an example of the environment affecting gene expression for many generations, as the next few generations of Daphnia will share their adaptations. Prader-Willi syndrome is caused by the deletion of between 4 and 4.5 million base pairs in chromosome 15 that came from the father. If the other version of chromosome 15 given by the mother were functional, this syndrome would not occur. But in the case of Prader-Willi, the mother's chromosome 15 has been epigenetically switched off through methylation during the formation of her egg. This results in children that are physically weak, moderately mentally challenged, small in stature, and have insatiable hunger in early childhood, which leads to obesity. Angelman syndrome is caused by the exact opposite genetic abnormality, with the deletion coming from the mother's side and the silencing from the father's. It results in severe mental difficulties, excessive laughter at unexpected times, hyperactivity, seizures, and aggressive behavior. Trauma has been shown to be a heritable trait. There were 1,700 pregnant women present during the attack on the World Trade Center. The women who were in their third trimester during 9/11 and developed PTSD as a result of the attack gave birth to children who are genetically more susceptible to developing PTSD themselves. For people who want to have children now, this is life-changing. Instead of just having to consider their health and choices during pregnancy, they now have to look at their entire lives up until conception for possible choices that could affect the health of their children and their children's children. People who were never directly exposed to Agent Orange, but whose parents were, are still having children with deformities. People who suffered from trauma like that of World War II and 9/11 are having children who produce higher levels of the stress hormone cortisol and are more anxious. Things that we used to believe only impacted people individually, we now know can impact their progeny for generations. Though this knowledge is unsettling, it can be taken as a real scientific reason for people to treat their bodies carefully and live healthier lives. For people who want to have children, their life choices are no longer just for themselves. This is a daunting revelation, but could lead to positive change in the lives of people who want to live healthily and now have a good reason to do so. Companies like Monsanto, who are responsible for chemical warfare like Agent Orange, also need to be held accountable for the damage they have caused in people's DNA, and the generations of people who have been affected after the release of the herbicide that was meant to clear vegetation during the Vietnam War, but as a side effect has led to millions of Vietnamese children being born with birth defects.